Right, class, let's talk about exponential functions. Now, exponential functions have this general form that I've written here, y equals a times b to the power of x. And you'll notice that the x in this case, in every exponential function, is going to be as an exponent. That's where this word comes from, exponential. It's saying, okay, the x is an exponent. Cool. You'll see here I've labeled the a and the b. The a, some people might refer to this as a starting value. I'm going to show you exactly how this translates into a graph during our practice problems, so let's not worry too much about it for now. The b is what I like to call the base, and that's the base of this exponential expression here, right? This is the thing that we're raising to the power of x. And you'll see I have two options labeled here. I have growth and decay. Growth is if this b is greater than 1, say if I had like 2 to the power of x, that means I'm multiplying 2 by itself some number of times, and the number's going to get bigger. Decay is when I have a number that's between 0 and 1, say like 1/2. If I keep on multiplying 1/2 by itself, it's going to get smaller and smaller. I'm taking half and half and half, etc. And that's going to decay. It's going to go down. So I've drawn two graphs here. You can probably guess this left one here. You see how it's going up as we increase x? This is growth. And likewise, if we're going down as we increase x, this is decay. Now you might have noticed this graph is not going down infinitely here. It's going to stop eventually. Well, it's not really going to stop, but it's approaching a value of y. And this line that I've drawn here, this red line, is called the asymptote. This is a line that the green graph is approaching. It's going to approach, but the key here is they're never going to touch. So when you see the word asymptote, think approach, but never touch. And the asymptotes that we're going to be working with today are all going to be of the form y equals something. Y equals some number. So like y equals 3, I'm just making up a number here. That could be an equation for an asymptote. So it's y equals a number. Okay, so let's do some problems here using that knowledge. You'll see here in this first category of problem, they're asking us about the features of this exponential function. And let's go through this step by step. So the function f of x is, well, even though I haven't taught you what a logarithmic function is, it's probably an exponential function. And we can see that because this x, remember, is an exponent of x. That's what makes it exponential. And it has a, let's think about our asymptote. Remember, our asymptote is that line that this graph is approaching but never really touching. And it looks like it's touching in this graph, and the thing is it's approaching this value of -6, but it's never actually touching it. Now this line that I'm kind of imagining here is a horizontal line. So this is a horizontal asymptote. And as I established, it's going to be y equals some number. Our number that we're approaching here on the left is -6. The range. Now, when we see the word range, we're thinking y values. The range of the function is, whoa, we have a lot of different intervals, so let's try to think about this. Our range, our y values, they don't go down forever, right? Our y values, they approach -6, but this is never going to equal -6. So that means if I were to write this in interval notation, it would look like -6. This open bracket means it does it never equals -6. Okay, and let's think about the upward bounds of our y values. Well, our y's go on, you see this arrow up here, this is going up infinitely. That means our upward bound is positive infinity. So this is our interval for our range. Okay. And it's asking if it's decreasing or increasing on its domain. Well, the graph, as you can see here, as we increase x, it's going up. So this is increasing on its domain. Now, I have these two arrows here, right? I have this arrow going to the left. So if we're talking, we did range up here. If we're talking domain, for the x values, it's going to the left infinitely. That means it's going to negative infinity on the left side. And on the right side, even though it looks like it's kind of tapering off, this graph is still going to the right infinitely. It's just going up really fast, but it's always going to go to the right. So that means the upward bound of the domain is infinity. So this is really the domain of our exponential here, and this is, if you don't recall, this is all of real numbers. And that makes sense, right? We can plug in any number into this function, and it will give us some y value, any real number at least. Here's our domain, the end behavior on the left side. Now let's think about what's happening here. On the left side, what's happening to our x values? Our x values are going infinitely to the left. It's going to negative infinity. The y values, well, the y values are approaching -6 on the left side. Remember, it's going toward -6. It's never touching -6, but it's approaching it. That's what this arrow means, approaches. On the right side, well, as x goes to infinity, x goes to positive infinity, the y is going super high up, right? Infinitely up. So that means y is approaching positive infinity. So we submit it. Cool. And that's our problem here. And you'll see here that they've drawn the asymptote of y equals -6. Okay, let's try another one here. This time we're going to graph this. And the good thing is, in this problem, they're giving us the table. But the first thing they're asking is for the equation of the asymptote. So this is really asking, hey, what y value is the function getting close to but never really equaling? Now you'll see on the left side here, we're going from 17 to 33. If we keep on going left, as we go more negative in the x direction, 17, 33, 65, 129, 257. It's going infinitely up, right? It's increasing more and more and more. So let's look on the right side. On the right side, we're getting really close, it looks like, to a value of 1. So that's my asymptote of y equals 1. Now, if we were to graph this, we would want to choose points with integer values. So I'm going to ignore all these ones with decimals, really. The first one I see here is -2, comma 2. So let's do that. -2, comma 2 is right here. -3, comma 3. -4, comma 5. So that's up here. And then -5, comma 9. And then it's going to ask us to draw this, which is kind of the annoying part. I would recommend using your finger for this. Whoa, that might not fly actually. So remember, we want to approach the asymptote but never touch it. That's pretty messy. I'm curious to see if it will accept this. It did not. It did not like my graph. Let's try another one here. But you guys are getting the idea, right? We're looking for, actually, I'm gonna look for a specific here. Perfect. Uh, you'll notice here on the left side, we're kind of approaching some number, right? We get smaller and smaller and smaller. It looks like we're approaching -4. So that's my asymptote here. And remember, I want to use integer values, right? So -4, comma 3 is a good one. Um, oh, my bad. That's -4, comma -3. I have -3, comma -2. I have -2, comma 0. I have -1, comma 4. Okay. And then if I try my best here, I'm gonna draw. Oh, geez. Undo. This is kind of what our graph looks like. The key with these, unfortunately, is you want to make it go through the 4 points, obviously, but you want it to approach but never touch the asymptotes. And you can draw it pretty close to the asymptote, as you saw me do here. Um, let's go back and try another one here. So This one's asking us to find the asymptote, and they're asking us to use technology. So that means Desmos or a graphing calculator of some sort is fair game. I'm going to type this equation in. 2 to the power of x plus 2, and you'll see something here as I do that. You see how the plus 2 comes out? What we're going to do here is we're going to make this parentheses x plus 2. It's a weird quirk of Desmos. So if you're trying to type in a exponent that's not just x, you'll have to do parentheses, I believe. But this is what our graph looks like here. And let's take a look. It looks like it's going up infinitely. It's exponential growth. And the asymptote then is the value that we're approaching but never touching. And you'll see here this graph is approaching, and it's actually going to eventually equal -3 on the side just because of rounding issues. You see how it says -3? That's just because Desmos is rounding it that close, but it's really approaching but never really touching -3. So that's our asymptote, y equals -3. And it wants us to plot 4 points. Um, so let's start with the y-intercept. It's 0, comma 1. Um, let's try. I can go to 1, comma 5. It looks like is a good one here. 5. Now, you'll notice if I go to 2, it's actually going to go beyond the bounds of my graph here. 2 comma 13 is unfortunately not something we can graph on this graph here. So we're going to need to go in the opposite direction. Let's go to -1. And that looks like it's -1. Let me rescale this here. -1 comma -1 is a point here. So let's use that. And then we need 4 points. So let's use -2 comma -2 down here. Cool. And that's going to ask us to graph this. So I recommend starting at the asymptote, going up through the points, and then going infinitely up. And hopefully it accepts that. Cool. Okay. So we've gone over how to identify features in exponential graphs and how to graph them. This next problem is going to require us to use a different type of formula here. You'll see I have here, I shouldn't say different type of formula. We're really using the same formula here, but we're being asked to convert it into a rate. Okay, so let's talk this one through. A new car is purchased for this much money. So that's our starting value. And it's depreciating at 5.75%. Depreciating means this is just a fancy word for loss. So this is really decay. And they're asking us for the value after 5 years. So what we're going to do here is we're going to set up our equation, and we're going to use these numbers here. Like I alluded to earlier, our A is our starting value, right? So our starting value in this case is the $16,500. So that's our A value. The thing is, though, this B value is not 5.75. First things first, we have to recognize, oh, this is a percent. So when I have a percent, what I'm going to do here is I'm going to, oh, sorry about that. I'm going to take my 5.75 and divide it by 100. And that's going to give me, well, if we think about divided by 100, remember we're just moving the decimal to the left twice. So that means this is really 0. Erase this here, 0.0575. This is what's called our decay rates. The value is going down, so it's decay, and this is the rate at which it's decaying. But even this is not really our B either. Our B is going to be equal to 1 minus the decay rates. So our B is really going to be equal to 0.9425. That's our B value. So let's actually plug these in here to our equation. So it's going to be y equals, oh, shoot, 16,500. And it's times 0.9425 to the power of x. You'll notice here I put the b inside parentheses. You don't really need to do that, but that's kind of how I like to write it out here. That means each year we're going to multiply by this number here, the 0.9425. And that is equivalent to a 5.75% loss per year. So when we multiply by this number, this is between 0 and 1. So the number here is going to get smaller as we multiply. And what we can do now is we can literally just plug in 16,500 times 0.9425 to the power of, in this problem, we're looking for the value after 5 years. So I'll plug in a 5. It becomes this. So after 5 years, so our x is 5, the y is 12,271, and we want it to the nearest cent. So I'm going to write it 3 of these decimals here because I want the nearest cents. Remember, cents are these two here. So I'm going to look at the 0 and then look to the right at this 4. Based on this 4, this is less than 5, so I'm going to keep this 0 as a 0. Everything else stays the same. This is our answer here. So you'll see the value. It started at 16,500. Now it's gone down to $12,271. So let's try another one. I want to actually try to find one where we have growth. Perfect. So we've talked about decay and the decay rate, and finding our B value was, in this case, here, tell you what, let me actually just draw another problem here, and then we'll talk about that in a bit. Okay, so town has a population of 9,000. Oh, I'm getting ahead of myself. So our starting value, the A value is 9,000. We grow 3% every year. So to find the growth rate, I'm going to call this R. We're going to take the 3 and we're going to, because it's a percent, we're going to divide it by 100. Percent per means division, 100 cent is 100, right? So our growth rate is 0.03. But remember, we can't plug this in directly into B, because if you think about this, if we multiply by 0.03 every year, it's not going to get bigger, it's going to get smaller. So our actual B value, the way we calculate this for growth, is 1 plus R. So it's 1 plus 0.03, which is 1.03. That's our B value. Now what we're going to do is we're going to make our equation. Looks like this. The A we said was 9,000. The the base is 1.03. That's to the power of x. Okay, and we want the population after 9 years. So that means we plug in x equals 9. 9,000 times 1.03 to the power of 9 is this number, and we want it to the nearest whole number. So what I'm going to do here, let me write this out. The nearest whole number, of course, is the number before the decimal. We look to the right. This 9 is 5 or greater, so that means this 2 is going to become a 3. Everything in this case stays the same. This is our answer. 11,743. Now let's think, does that make sense given what we have here? Remember, we started at 9,000 and our number has gone up. And that makes sense because we're growing. So let's submit it. There we go. Now, I want to address a pattern that you might have noticed here in that when we had uh, a percent, we calculate the rate. Oh, sorry. The rate was the percent divided by 100, right? And when we had growth, our b value was 1 plus the rate. And when we had decay, our b value was instead 1 minus the rate. So that's the general pattern we use here in these problems. Let's try some other ones here. Actually, you know what? I'm going to jump to this section here because this is similar. Um, we're looking for the excuse me. We're looking for the growth or decay percentage. And given what we just learned here, we can kind of do what we did, but do it in the opposite direction. I have some notes already written out up here. Um, so let's first look at the b value, because if we're looking for the percentage rate of increase or decrease, we don't really care about the starting value, unfortunately. This b value, it's 0.51. This is between 0 and 1. So this should be decay, right? Now, the decay rate is, remember, we did this a different way, right? We found the b value by doing 1 minus r. But if we instead solve this equation for r, we get b minus 1 equals negative r, and then r is 1 minus b. So what we're going to do is we're going to take, to find the rate, we're going to do 1 minus the b value. Uh, and that's the equation I have up here. Decay rate is 1 minus the b value. So let's do this real quick. For this one, r is 1 minus the b value of 0.51. That means our rate of decay or decrease is 0.49. But that's not a percent. To get the percent, we have to take the rate and then we multiply it by 100. Remember, we did this the opposite direction, where if we were trying to find the rate and it was the percentage divided by 100. This time, to get the percent, we multiply the rate by 100. So in this case, it's 0.49 times 100, and this is 49%. So plug in 49%. Remember to change this to decay if it is decay. And that's it. Let's try another one here. Let's look at this. We're looking for the percentage rate of increase or decrease. In this case, 1.01 is greater than 1. So we should expect this to be growth. And our problem is going to be slightly different because we have growth, but not too different. When we have growth, if we're looking for the rate, we want to do b minus 1. So when you can think about this, if this number here inside the parentheses, if the base is bigger than 1, we want to subtract 1. If it's smaller than 1, we subtract it from 1. But yeah, in this case, it's 1.01 minus 1. The rate is 0.01. Remember, we want to convert this to a percent, so we multiply the rate by 100. So it's 0.01 times 100. So this is a meager 1% increase. And that's how we do these problems. Cool. Let me show you how to find exponentials from 2 points. So that's literally when we're given 2 points and we want to find a function. So let's do that now. Let me go ahead and clear this out. So I have somewhere to work. Okay. Excuse me. In this problem here, we're given 0, comma 14, and we're also given 8, comma, wow, 3, 5, 8, 4. There's a few ways to do this, but I'm going to show you the algebraic way because you guys are a pretty algebraically minded class. we have sets of x and y values, right? And we can plug stuff in here to solve for the value and for the b value. Now, what I'm going to recommend we do is if we have an x value of 0 like we do here, let's use that first. So we have x and y, so I'm going to replace my y with 14. I'm going to keep a, I'm going to keep b, and I'm going to replace the x with a 0. Now, if we recall our exponential or our exponent rules, b to the power of 0, or really anything to the power of 0, is just 1. So this is really 14 equals a times 1. And that means a is equal to 14. So this makes our job of finding a really easy. So we found a. Now we're going to use the other set of points here. So that means I'm really going to, here, let me draw it like this. 8, comma, 3, 5, 8, 4. We now have an x and a y value here that let's plug into our equation. Y equals a. Well, a, remember, we know now is 14 and it's b to the power of x. So let's replace x and y. It's 3, 5, 8, 4 equals 14 times b to the power of 8 in this case. So first thing I'm going to do if I'm going to solve for b, I'm going to divide both sides by 14. I would type that in. 3584 divided by 14 is 256. And that equals b to the power of 8. Now, if we're going to solve for b now, we're going to take the 8th root of 256. Another way to think about this is we raise it to the power of 1 over 8. So what I'm going to do here is I'm going to type in 256, and I can raise it to the power of 1 over 8. And that gives us 2. So our b value is equal to 2. So we found our a, we found our b. Our equation is now a b to the power of x, which because a is 14 and b is 2, this is our answer here. So y equals 14 parentheses 2 to the power of x. To get the exponent, I'm holding shift and pressing the caret or the 6 key on my keyboard. Okay, and these ones are all pretty similar. They give you the y-intercept, the 0 comma something, and that's going to give you your a value. Let's go over a problem where they don't do that. Now they're asking for they're not actually asking for a function, but it's going to be a bit easier if we find the function. They're telling us it's of this form, and they tell us 2 points, but they're not writing them like points. They're telling us when x is 3, y is 7. So that's really just a more complicated way to write a point, but we can solve it similarly. Okay, let me clear out here, clear out here. Okay, now we have f of 3 equals 7, and we also have f of 10.5 equals 23, I believe. And they're telling us, okay, it has to be of this form, y equals a b to the power of x. Now, like I said earlier, this number inside the parentheses, this is our x value. This number here is our y value then. So likewise, we have x and y. We have 2 sets here. So let's plug them into our equation. Now, our y in this case is going to become 7. Our a is the same, b is the same, x is going to be 3. Now you'll notice here, we no longer have b to the power of 0, so we can't just cancel this out like we did earlier. So let's leave that alone. Let's find our other equation. In this case, our y is 23. Our a is the same, the b is the same, the x is 10.5. So you'll notice here we have two equations and two variables we're trying to solve for, a and b. So what I'm going to recommend we do is we're going to solve this system, but it's going to be unlike how we've solved previous systems in the past. What I'm going to do here is I'm going to put my two equations on top of each other. I'm just choosing to put the bigger numbers on top. This is personal preference, really. I think it makes it a bit easier. These are our two equations. Now you'll notice they both share an a. So the weird thing I'm going to do here is I'm going to divide the left sides by each other and divide the right sides by each other. And let's see what happens. So left side divided by right side, this is going to be 23 over 7. Uh, when we divide the right sides, the a's cancel out. I really should use a different color for this. Let me do that now. Um, we got 23 over 7 on the left. These a's cancel, and we have b to the power of 10.5 over b to the power of 3. And when we have exponents, when we have powers like this with the same base, and we divide them, we take these exponents and we subtract them from each other. So this is really b to the power of 10.5 minus 3, which is really b to the power of 7.5. And it equals 23 over 7, which is gross. Now, to get rid of this exponent, we're going to raise both sides to the power of 1 over this exponent. So we're going to raise both sides, again, to the power of 1 over 7.5. Um, and that's going to give us our b value. It's going to be really nasty, but that's okay. Let me clear out this, clear out this. I'm going to type in my fraction, 23 over 7. I'm going to put it in parentheses. And I'm going to raise this to the power of 1 over 7.5. And this is our b value. Gross. So they're asking us to round this, so it doesn't have to be perfectly exact, but that's kind of our. I'm just going to write this with a bunch of decimal places, and that should be good for now. Because we're ultimately gonna, well, we're gonna use the calculator. Spoilers. Let's go back to our original equation here. Now we found b. We still need to find a. We don't know what a is yet. So just like we did with systems of equations, linear systems of equations, we have the b now. We can plug that in, and we can solve for a. So let's do that with this equation here, just because it looks a bit simpler than the other one. Um, so we have 7 equals a times b to the power of 3. In this case, b is this big mess, and we raise that to the power of 3. We want a. So a, to get a, we're going to divide by this big mess here on both sides. I am now regretting choosing to write so many decimal places. These cancel. So our a is 7 over 1.17188 to the power of 3, which of course we're going to plug into a calculator to get. Um, Now something you could do here if you wanted, you could say b equals. That's our b value. Now a is equal to 7 over b to the power of 3. I could alternatively type it in 1.17188 power of 3. Oh jeez. Here we go. And it'll give us a similar answer. The more accurate way to do this is actually by plugging in the variables like this. So we have our a, we have our b. A is 4.34956. Okay, cool. So we did all this work, found the A and the B. But the thing is, please don't, for this level 2 stuff, don't plug in y equals a b to the power of x. So that's not the answer. Remember, we're looking for when f is 9 point, I'm sorry, f when x is 9.5. So we're looking for the value when x is 9.5. The way we calculate that is we can now that we've defined a and b in the calculator, we can write a times b to the power of 9.5, and it will tell us the answer here. It will calculate it for us. If you really want to, if you really hate yourself, you can plug in this with the actual numbers, because that's really what the calculator is doing. The more accurate way is to plug it in like this, because this is using the exact values of a and b. Anyway, if you plug in enough decimal places, though, it should give you something accurate enough. We want it to the nearest hundredth, so our answer is 19.6. If I want the nearest hundredth, I'm going to choose to take 3 digits after the decimal because I want this one. I'm going to look to the right. 6 is 5 or bigger, so that means this 2 becomes a 3, and that's our answer. 19.63. Okay, so congratulations, you know how to do what is, in my opinion, the hardest type of problem on this problem set.